So today we are going to further explore this idea that some of you have already been noticing, that when you have this kind of cyclical or repeating pattern, it's finding the integral, finding the derivative, finding the integral, finding the derivative. So why don't we just do it all at the same time? And some of you even notice that the signs alternate back and forth. So there's actually a method called the tabular method for repeated integration by parts. Okay, so it's just a way of organizing what we're doing here. And you can use this to integrate the following forms, which hopefully you're pretty familiar with now. We have x and then e to the x here. And then we have x and sine x, and then x and cosine x. So I changed this order around a little bit. The book starts with writing down alternate signs, but if you don't know how many rows you need, that really doesn't help me. So what we're going to do is repeatedly differentiate u until you obtain 0. And so you still have to find u, and then it says repeatedly integrate v prime. And v prime is also what we know as dv, and I think that's the language we were using last time. Then you write down the alternate signs, and then you're going to multiply column 2 by column 3 following the arrows, and I'll show you where those arrows are in a second. So here, our first example is the integral of x squared times e to the 3x dx. So we still want to find u and du. So u in this case is going to be x squared. We also want to find dv now. And it's e to the 3x. Now for the e's of this, we're not actually going to write our dx. We're just going to assume it's there all the time. When they ask you for what dv is, you do want to write. But in a tabular method, right, this is just for speed and ease of use. And then the final answer is what we're looking for. So first thing you want to do is look in this column and find all the derivatives of u down to 0. Okay, so x squared, derivative is 2x, derivative of 2x is 2, derivative of 2 is 0. And since this is pre-planned, the boxes fit perfectly. Okay, it's not going to happen like that, obviously, in your assignment. Next, we want to integrate e to the 3x, okay, as many times as we had to derive u. Okay. So integrate e to the 3x. So we want to think about that e to the u du type of situation. Okay. So you can use this over here for scratch work or whatever. So if we have integral of e to the 3x dx, that's going to be 1/3 e to the 3x. So we see that du was 3. So we had to put the 3 in here and the 1/3 out here. So we do get 1/3 e to the 3x. And when you're looking at e to the whatever, we're going to have a pattern as we keep integrating this, right? Because the constant in front doesn't actually change the integral. It's just the factor in front. So it's going to be 1/3 times 1/3 e to the 3x, which would be 1/9 e to the 3x. Okay, did everybody get that?
So is it 1 is the derivative of the u to the power of however many u's there are? I think it made sense. Right, like for the
Which part?
coefficient in front,
Coefficient.
would you take the derivative of
Derivative of u,
yes
of this
derivative
u,
of
the 3x.
yes, and then put that to the power of n, which would be representative of.
How many times do you have to do
You
this?
have that minus 1.
Yes.
Right.
So this would be 1/27 e to the 3x.
Is this all we're doing?
Mm-hmm. Now, for the alternating signs thing, we're going to start with positive, and then we go negative, and positive.
Why?
And
Do it always start with
Do you
positive?
always do?
Always start with positive. And then alternate the signs.
Just like that.
Yep, just like that. The reason is, if we think back to our formula for integration by parts, remember it was uv minus the integral of v du. So that's why you do minus the integral. So that's why the second one is minus. Okay, and then if you have to keep doing integration by parts the second time, you're going to have minus a minus, which is going to be positive. The next time will be minus a minus a minus. We're just back to minus. Okay.
Oh my gosh.
So here's how we do this now. If we think in terms of the integral, we're going to end up following these arrows. So this positive sign is going to apply to this x squared. And then this x squared is going to multiply by the integral of v prime. Okay? And that becomes the first term in our answer.
Wait. Oh, because it's D.
So positive x squared times 1/3 e to the 3x.
Wait, is that because that column is D?
Yes, this was dv.
That's originally DV and then it's VB.
V, capital V, so on and so forth. All right, so there's our first term. And you just keep going down in the same manner. So this negative is going to apply to the 2x. And then it's going to multiply by, diagonally, 1/9 e to the 3x. Here's your minus.
So this is just a more like...
It's just a structured method for finding all the derivatives and all the integrals and then combining them all at once.
So this is like faster?
Faster.
This would take forever to do next before.
Okay, and then the last one, the positive applies to the 2. And then the 2 multiplies 1/27 e to the 3x. Okay. Now this last one, if the derivative is 0, notice if we multiplied, it'd still be 0. And so there's nothing more to do here. And all we have to do is simplify this. So all in all, we're going to put our fractions first, 1/3, then our x's.
Well, you get 3x, right?
No.
Why not?
Because you do
Oh,
yeah, all 1/3. Say plus 3.
you can do that, yeah.
And then at the end, we have our plus c.
Now, could you pull the third out since it doesn't matter what the coefficient is?
You can pull an e to the 3x out, and you can actually pull 1/27 e to the 3x out.
Yeah.
And for me, if you get it to this form, that's fine. Sometimes the answers in the book, depending on who wrote them, they like to factor out the greatest common factor. Sometimes they don't. But if you can get it to this, I will be happy. All right, so let's go ahead and work through letter B together here. So we have the definite integral of x squared sine 4x dx. Because there's an x and a sine, we are going to let u equal x squared. And that means dv is going to be everything else, which is going to be sine 4x dx. All right, so let's go ahead and fill out u and its derivative right here. So u is x squared, and moving down, its derivative is 2x. The derivative of that is 2, and we continue all the way till the derivative equals 0. Next, let's take a look at v prime. So v prime was sine of 4x. And again, we don't have to write the dx part because we know it's there. Okay, so let's do some work over here on finding the antiderivative there. So we want the integral of sine of 4x dx. And so for this one, we would let u equal 4x, and that means we need du on there, which would be 4 dx. So that's going to mean placing a 4 on the inside and a 1/4 on the outside. Okay, so when we do this now, we have sine u du. So the integral of sine is negative cosine. So we're going to have negative 1/4 cosine of 4x. Okay, so there's our first antiderivative, negative 1/4 cosine of 4x. And now we need to integrate that. So we're going to take the indefinite integral of negative 1/4 cosine of 4x. And you'll remember we want to take out our constant. With respect to x. And we can take out that constant, so we got negative 1/4 times the integral of cosine 4x dx. And the same thing is going to happen here, where we're going to let u equal 4x, and so we need 4 dx to make our du, which means we need another 1/4 on the outside. And when we integrate this now, the antiderivative of cosine is just sine, so we have negative 1/16 of sine of 4x. Okay, so we'll put that one in there. And now we want to integrate this one. So we want the integral, and we'll put negative 1/16 on the outside because we can do that right away. And now we have of sine 4x with respect to x. And notice now this part right here is the same as what we did on the first part. So we have this idea that it's going back and forth. So the 1/4 and the 4 needs to happen again down here. So we'll put in the 4, we'll put the 1/4. And so now we have, let's see, the integral of sine is negative cosine. So now we're actually going to have positive and 1/64 and cosine of 4x. Okay, and that's our last one here. Okay, so looking at this, you could have done it a little bit more quickly than what we did. You can notice that going from sine to cosine changes the sign, and then with the 4, you're going to have to put a 1/4 right there. For our next one now, cosine to sine keeps the same sign, so the negative has to stay the same, and because of that 4, we're going to multiply by another 1/4, making that 4 turn into a 16. And then the same pattern happens again. Since we're going from sine to cosine, we change the sign because it's negative. And because of that 4, we're going to multiply the 16 by 4 to get our 64 there. All right, now that all of our work is done, again, remember we want to alternate our signs starting with positive. So positive, negative, positive, negative. And then we want to follow our arrows. So apply the positive to the x squared, and then multiply the x squared by v, which is right there. And we'll follow these arrows all the way across. And now we can come up with our final answer. And we can put all this in order. So we have the positive times x squared times negative 1/4 cosine 4x. That's going to be negative 1/4 x squared cosine 4x. Then we have a negative 2x times negative 1/16 sine 4x. So that's actually going to be positive, and then 2 over 16 is 1/8. So 1/8 x sine 4x. And then our third term here, positive 2 times 1 over 64. So that's really 1 over 32. So plus 1 over 32. There's no x's this time. And cosine 4x. And last but not least, because it's indefinite integral, plus c. All right, I want you to give letter C a try on your own. Go ahead and pause the video and come on back when you're done to check your work. All right, welcome back. So you should have let u equal x to the 4th, and here are all the derivatives there. And then dv should have been e to the negative x. And you'll notice when you take the integral of e to the negative x, you have to have that negative there, and so it keeps alternating on the outside. Okay, and then you just simply follow your arrow pattern and multiply your pluses and minuses here. And so your final answer should come out with this right here. Alright, so that is using the tabular method for repeated integration by parts. Alright.
What's that stuff you did in the red on the left?
This right here?
Yeah.
This was dealing with finding this column.
Can you go through finding antiderivatives of e, just like maybe generally?
Like we did at the beginning of class?
Yeah. I get super mixed up.
Yeah, so this is what we're looking for. E to the u du, and it just equals e to the u. So what happens, if we just had e to the x dx, that's just e to the x.
Right.
Now as we put something up here, like 2x, okay, now we don't have u du, because u is 2x, and du would be 2 dx. So you can see our u's right here. And then du, we have a dx, but we need an entire du. So we got to put that in right here. Okay. Now, to make sure that everything's still balanced, if we multiply something by 2, we're going to have to multiply by 1/2 to balance it out. Now, if we rewrite this, we can see this as 1/2 times the integral of e to the u du. Okay, you see how 2 dx equals du, so I'm just replacing those two with du, and then the 2x is just u right there. And now if we just go to our basic formula, right, the integral of e to the u du is just e to the u. So we know the 1/2 stays in front, then it's e to the u. Then all we're going to do, again, is substitute in for u,
Back in.
and we're going to substitute 2x back in there.
If when was it that you just did e to the same thing, whatever it was, and then did like a chain rule type thing, and multiplied that entire thing by the derivative of the exponent? Is that finding the derivative?
That's finding the derivative. So finding the integral, you're going to multiply by the reciprocal.
The reciprocal
of the derivative.
Of the exponent.
Yeah.
Okay.
Yeah. So
That's easier for me to
So-
comprehend instead of all the steps you did.
yeah. So it's really 1 over the derivative
Okay.
of u.
Okay. Okay. That's,
Okay.
Yeah. Thank you. Perfect.
So I guess we could do that.
That's just what I needed.
So you just add that little part in,
Okay.
and then you're good to go.
Thank you.
Cool.